Okay, this new section is very short. It's entitled The Axioms of Probability. The first axiom says, for any event E, the probability that E occurs is always going to lie in between 0 and 1. If P of E is in fact 0, that means it won't happen. E will not occur. It will not happen. Okay, the probability that it will snow during the summer is 0. If the probability of E is 1, this says E will happen. Okay, there's no question about it. It will happen. You will go to work tomorrow. Or assuming that it's light out right now, that is, the sun rose this morning, it will be light in 20 seconds from now, it'll still be light. That's going to happen 100% of the time, assuming it's mid-afternoon or mid-morning or morning. It will definitely happen. Most events, the probability that they occur will be between 0 and 1. The probability that if you toss one single coin and you get a head will be a half. Of course, 1/2 is between 0 and 1. Statement or axiom number 2 is, let S be the sample space of some event. The probability that S occurs, that is, the probability that at least that one of the events in the sample space came up, is 1. For example, if you toss a coin, you either get a head or you get a tail. Well, the probability that you get a head, or, that means plus, the probability that you get a tail is 1. Well, stretch it out a little bit. The probability you get a head is a half, plus the probability that you get a tail is the other half, and when you add them up, you do not get what I was about to write, but instead you do get 1. If you roll a die, the sample space would be either you get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. The probability of getting S, that is, the probability of getting a 1 or 2 or a 3 or a 4 or a 5, all the way up to getting a 6 is 1. If we claim that in terms of weather, it's either sunny, cloudy, or raining. Suppose those are the only 3 types of weather. It's sunny, it's cloudy, or it's raining. But you know, I don't like raining because it can be sunny and raining. So suppose we were to remove raining. Either it's sunny or it's cloudy. Let's go with that premise. Well, then the probability of S would be 1. 100% of the times during the day, if you look outside, it will either be sunny or cloudy. That's the second axiom. You add up all the different probabilities they will add up to 1. Add up all the probabilities in a sample space. In the sample space, it will add up to 1. The next one is rather important. But first, okay, the third axiom, like I just said, is rather important. And basically, it says that if event E1 and E2 and E3 forever and ever and ever are mutually exclusive. What does that mean? That means any two of these events, E1, EI, and EJ, the intersection will be the empty set. Of course, if I and J are the same, it won't be. That is, if you take any two different ones, you take any two different ones from this infinite list, guarantee you the intersection will be the empty set. So then, the probability of the union of these mutually exclusive events, the infinitely many exclusive events, will equal to, well, you can just add up the probability of each one. Probability of E1 plus the probability of E2 plus the probability of E3, etc. That is, this index I can go from 1 to infinity. These add up to infinity. Okay. So that is axiom number 3. I want to prove a little theorem. E is equal to E union nothing else, the empty set. If you have set E and you add on nothing, you get E. So the probability of E is equal to the probability of E union the intersection. I guess I really can't do this yet. We didn't argue this theorem yet. But this is going to be the probability of E plus the probability of the empty set. That is, the probability of E equals the probability of E plus this. Remember, the probability of E is some number. Say it's 0.7. 0.7 is equal to 0.7 plus the probability of the empty set. Well, you should know what you add to 0.7 to get 0.7. 0.7 is equal to itself plus 0. The probability of the empty set is 0. Okay, we'll be able to prove that more rigorously in another section or two. So, a consequence of this third axiom is we can take a finite union. We can take a finite union and say the same type of statement we did above. That is, let E1, E2, up to En be mutually exclusive. They have nothing in common. Any two of these have nothing in common. If you think about it, if two of them have nothing in common, well then three of them will have nothing in common. For example, EI intersect EJ intersect EK will also be empty. You should have learned somewhere in set theory that it has the associative law. That is, I can put brackets around those two. But by definition, since they're mutually exclusive, this is the empty set. Well, to be in the intersection, you have to be in both. What's in the empty set and EK? The answer is nothing. If you have one set that has nothing, and you have another set that possibly has things, what do these two sets have in common? The answer is nothing. Remember, this symbol is the same as that, the set that has nothing. So it's not just any two, it's any number of these sets, more than one, will definitely have an intersection being the empty set. That's what mutually exclusive means. Okay, so now I guess this argument will be hand-waving a little bit because I have yet to prove that the probability of the empty set is 0, but I'll state this theorem or the fact nonetheless. Let E1 through En be mutually exclusive. Then the probability of the union of the EIs as I goes from 1 to n, this will equal to the summation of the probabilities of the EIs as I goes from 1 to n. Now, why is that true? Well, if you look at the top, what if those EIs were E1, E2, eventually you get to En, and then En plus 1 is the empty set, and the next one is the empty set, and the empty sets go on and on forever. Okay, so let's look at this some more carefully. Erase this, please. Okay, so let's look at this. That's the same as the probability of the union of the EIs as I goes from 1 to n. And the reason is, you take the union of all of these, and then forever and ever you're adding on nothing else. Well, then you just get the union of all of these. Adding on the empty sets doesn't affect the union. That is, what's in between these two brackets, if whenever n is bigger than, whenever the subscripts are bigger than n, you get the empty set, then what's in these brackets is exactly what's in these brackets. Now the other side. This says it's the probability of E1 plus the probability of E2. Eventually, you'll get to the probability of En plus the probability of En plus 1 plus the probability of En plus 2 forever. But these are all 0. So basically, all you get is what that is. And that's the summation of the probability of EIs as I goes from 1 to n. So this third axiom allows this statement here. You can even have a finite union. It won't matter. It won't matter if you have a finite union or an infinite union. You can always make a finite union equal to an infinite union. Just add on the empty sets. Just add on the empty sets forever. One last example. If I ask you, what's the union of 1, 2, with the set that has 1, well, Okay, 1, 3, 4, union with the set 7 and 8. 7, 8, and 2 and 3. Well, can I make, and that, keeping the same answer, well, they have to have 1 and 2. It has to have 1, I already wrote it. It has to have 3 and 4, the union. The union has to have 7 and 8. And the union has to have 2 and 3, but I already listed it. That's the union. Okay, can you give me an infinite, or a union of infinite sets that also have the same union? The answer is not unique. There's many different ways of making this an infinite set that still has the same union. For example, I can keep adding on 1, 2. Union 1, 2. Union 1, 2. Okay, but that's not what I want to do. I'll just union the empty set. I'll just union it with the empty set forever and ever. There's an infinite set. And what does this union equal? The answer is the same thing as before. So anytime you have a finite union, without changing the results, you can come up with an infinite union. And that's what the last statement, the last consequence we talked about, the one that was a consequence of axiom number 3. Okay, this completes the section on the axioms of probability. You really need to know these 3. They're very important.